Fermat's theorem says if f has a relative max at x equals c and the derivative exists, then the derivative is 0. What we could rephrase it as if f of c is a relative max, then, well, what do we know? We either know that the derivative exists there or it doesn't. If it doesn't exist, it doesn't exist. If it does exist, Fermat's theorem tells us that it's 0. Agree? Okay, so I'm ready to say that if f of c is a relative max, then either f prime of c does not exist, or f prime of c is 0. Does everyone see how that's like the same thing? Mark, can you erase the backboard? Because if it doesn't exist, it doesn't exist, and if it does exist, we just proved it must be 0. So in other words, it either doesn't exist or it's 0. Okay, this is powerful information. What we have just learned is that if a function has a relative max somewhere, then there are only two possibilities. Either the derivative doesn't exist at all, or the derivative is 0, and there is a horizontal tangent line. Which means, was our overall goal for today? Our overall goal today was we were hunting for extrema, right? And we said that there are only two places to look for extrema. At the endpoints, and at the relative extrema. Alright, well we've now solved the second problem as well, or almost. We've kind of almost solved it. Because where should I be looking for relative extrema? Places where the derivative is 0, or places where the derivative does not exist. These places are so important that they get their own names. They are called critical values, or most people just call them critical points. Critical points are places where the derivative is either 0 or does not exist. And if you find all the critical values, then the relative maximum and minimum must be among them somewhere. Okay, we're going to switch to this other board. Can you close the window and close all the blinds so there's no glare over here? We're going to do two problems. Let's go. I am going to give you a function. Here is the function. X minus 2 sine x. And we're going to look at this function on the interval from 0 to 2 pi. And the second problem is going to be f of x equals x to the 3/5 times 4 minus x. And we're going to do this on the interval, I forget. -1/6. Okay, go. Begin. Find the task is find the absolute, I got it. Find the absolute extrema of this function on this interval. That's good enough. And welcome period 6 and 9, you're watching the video. Let's move over here. What are you guys going to do first? Okay, that's one thing you could do first. You could take the derivative first. Okay, so did you guys take the derivative? Okay. Bueno. What do we get? What is that, like 1 minus 2 cosine x? Agree? Okay, so what should we be looking for? Fast, fast, fast. What should we be looking for?
When it freaks out or if it equals 0.
Exactly, when it freaks out or if it's 0. Is there any place where this derivative is freaking out? No, so we don't have to worry about that. So we basically want to know, all right, when is 1 minus 2 cosine x equals 0? Did you solve this yet? This is happening whenever 2 cosine x equals 1, so that's when cosine x equals 1/2. So that's at pi over 3 and 5 pi over 3. You good? Agree? Agree? Okay. Okay. What should we do next? So these are the critical values. Critical values. What should I do next? Berkowitz says, actually, this students find this a little bit confusing, at least possibly at first. Do I know at this particular moment that these are relative maxima or minima? No. What do I know about them? They might be, okay? That's the entire reason why we've invented this thing called critical values, right? Critical values are things that might be relative maxima or minima.
Wait, why don't we know that?
We just don't quite know yet. I suspect that they are. In fact, they are. I'll just tell you between you and me. But you don't know that yet. We haven't analyzed it. We haven't determined that yet. Because notice the logic of our theorem is sort of important. Our theorem, the slight rephrasing of Fermat's theorem, says if there's a relative max, then the derivative is 0 or does not exist. So what we do is we collect all the numbers at which the derivative is 0 or not existing. And then we know that if there are any relative maxima or minima, they must be among these numbers. Does everyone have the logic straight?
It's like you were saying, like the converse doesn't work.
The converse doesn't work, yeah. Okay, good. And Berkowitz says we better plug these in, so let's do that. What is f of pi over 3? It gets a little bit ugly, I guess, right? It's like some crap. Pi over 3 minus root 3 over 2? No. 2 times root 3 over 2. So just root 3. Okay, so can I just call pi over 3 like about 1-ish? Yeah, so that's like 1 minus root 3. So I'm going to call this about like negative 0.7 because that's more or less what root 3 is like 1.7. Who is with me? Everyone say everyone. F of 5 pi over 3 is going to be 5 pi over 3. What is the sign? What else? What's the sign of 5 pi over 3? It's like negative, right? So this would be like negative 2 negative root 3 over 2. So that's more or less like plus root 3. Can I call that basically 5? Yeah, so that's like 5 plus root 3, so that's like 6.7 or so. Okay, are we good? All right, so we found that. What else must we do? Do not forget the endpoints. Yeah, we must check the endpoints. So what happens when you plug in 0? What do you get? 0. What happens when you plug in 2 pi? You get 2 pi. Okay, so I'm prepared to announce right now what is the absolute maximum of f on the interval 0, 2 pi. What is the largest y value on this interval? Oh, it's a little bit close, but I think it's going to be the f of 5.3, right? Yeah. So it's going to be 5 pi over 3 plus root 3. Okay? And what is the absolute minimum of f on the interval 0, 2 pi? What is it? It's just 0, yeah? Say yeah. I think? No. No, it's the oops, sorry. Pi over 3 minus root 3. Terrible marker.
it all on one.
So, good. By the way, this is a function that we used to know how to graph-ish in pre-calc C or pre-calc B even. Can I get a purple or blue behind you? So, because what do we know about this? We know that sine x is between -1 and 1, right? Say right.
Yeah.
We know, therefore, that like -2 sine x has to be between like, what the hell is that? -2 and 2, I guess, right? Yeah, but like the other way around. Okay, and then, wait, is that fine? Yeah, because it like flips, and then I just like flipped it back, yeah. And then I can also add x to all three sides of this. So x minus 2 sine x has to be between x minus 2 and x plus 2. In other words, if I wanted to make a really good graph of this function, and I do, then I know that it's like going to be bounded between, let's see, this is like pi, this is 2 pi, so 2 is probably like around there-ish, or so, and so I know that, that the line x minus 2 and the line x plus 2 is like a envelope for this thing, right? Okay, and now let's plot this. At 0, it's 0. At 2 pi, it's 2 pi. And previously, oh, we can also plug in like pi. If we plug in pi, what do we get? Answer, pi. Right? And back in pre-calc C, we were just content to just be like, well, you know, it kind of goes like up and then down and up and kind of just waddles in between these two lines. Everyone agree that that's pretty much what we did back then, right? Now, with the power of calculus, we know things. We know that something very exciting is happening at pi over 3, which would be like over here-ish. That this number is, that there is a horizontal tangent there. That's because it's a place where the derivative is 0. So I feel, give me a green, I feel that the derivative, if the ah! Okay, I feel that the derivative is 0 there. We also know, wait, stay with me. We know that the, at 5 pi over 3, we know that the derivative is a little bit, it's like a little bit up here-ish, right? It's a little bit bigger than it is at 2 pi. So also here, the derivative is 0. So when it comes time to graphing this function, I think I now know a lot about this function. I know it's 0, and I know it must go down, and then up, and then probably I need to like touch this somewhere. Is it going to be at something? Well, I have no idea. When's it 0? Is that easy? No, it's not. Then we're gonna go like up here, something. This is actually kind of hard. And then back down and something like that. Blah, blah, blah. That looks kind of terrible. But I know that, so James, now that I've kind of thought this through, I've decided that there must be, in fact, a relative min there, right? Because that's the only way for that to be a horizontal tangent, for me to start at 0 and then go down. And the only way for me to have a horizontal tangent here is if that's a relative max. Okay, everyone get it? Good. I think the second example is also really important, but I think we ran out of time. Did anyone get anywhere on it?
No.
What's interesting with this one is you do get some places where the derivative doesn't exist. Let's just do it right now. We got 2 minutes. Screw it. How should we do this? Product rule?
Yeah.
Okay. So the derivative is the derivative of the first, which would be 3/5 x to the -2/5 times the second, 4 minus x, plus the first times the derivative of the second, which would be -1. Okay, that wasn't too bad. Now I have like a whole bunch of gross. So there's a secret trick. And the secret trick is factor out the one with the lowest power. So factor out x to the -2/5. If you do that, what do you end up with? 3/5 times 4 minus x minus, he says this is x, is he right? Yeah, because something to the negative 2/5 times something to the 1 is something to the 3/5. And notice how everything in here is really chill. In fact, does everyone see that? In fact, if I multiply by 5 over 5, that's like a really good idea. So then I can say that this is really like x to the negative 2/5. And then just like take out a fifth or whatever, right? And so then this is 3 times 4 minus x minus 5x. See how by crafty factoring, I have now turned this problem into like a much easier problem, right? Because now that's just linear in there. So what is this? This is like 12 minus, did I do something wrong? No. Yeah, 12 minus 8x, really? Yeah. Okay, so, over, I swear that's like something went wrong.
No, you're good.
Really?
Yeah. Real Mr.
5 over 5, okay. 12 minus 3, yeah. Alright, over 5, and now this is like x to the 2/5. Alright, so, I guess we can factor out like a 4 in the top. Yeah, no, it is worth it. Well, okay, maybe, well, yeah, I'm going to do it. Yeah, so I factor out a negative 4 up there, and I get 2x minus 3 over 5x to the 2/5. I swear I'm making an algebra mistake, but people are telling me I'm good. Okay, what are the critical points for this function? Quick before I turn the camera off. Yeah, the critical values are where the derivative is 0, which is 2/3, but also where the derivative does not exist, which is 0, because it's put 0 in your book. 3/2. Alright, good, goodbye. Turn off the camera, please.
Where's the off button?
Yeah, exactly.